Hello, I welcome you all to this another interesting screencast, and the problem reads the distribution of soil loading on the bottom of the building slab is shown. Replace this loading by an equivalent resultant force and specify its location measured from point O. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by RC Hibbeler. So we have a slab, a building slab, and on top of the slab we have some engines there that this particular slabs is supporting, and as a result of the forces, okay, the weight of each one of these engines that they are exerting, okay, the soil underneath this slab also reacts. So we have this reaction force from the soil, all right, which is distributed, right? So we have this distribution combination of rectangular and triangular loads, and we have been asked to replace this loading by an equivalent resultant force and specify its location measured from point O. So we are going to rewrite this distribution force in shapes that we can easily work with, which are the rectangular and triangular distributed force. So let's do so. So I'll have one from here, sorry. So I'll have one from here, which is 50 up to here. From here up to here. So this is one of the components. Then I'll have another one from there like this. This is triangular. Triangular. Then I'll have another rectangular from there to there. All right. Then I'll have another one which is triangular. I mean the one in green. The one in green is rectangular, and then this one is triangular. The one in yellow. So we have two rectangular in red. I mean two rectangular in red and in green, and two triangular in blue and in yellow. So let's now apply some equivalent forces for each one of those. The red will have an equivalent force that will be placed at the mid span. Okay, let's put it somewhere there. I think this is more of a mid span there. All right, and then we are going to have a triangular. Let's say it is somewhere there. Okay, and then let's say we have at the mid span this rectangular somewhere there, and we have the last but not the least for this rectangular somewhere there. All right, great. I think everything is visible. I think so. So now we'll need the dimensions with reference to mainly from O. This is where I'm interested, but I can also indicate that side, no big deal. So these are the dimensions. We'll be interested in these dimensions. All right. Great. So let's add some details. Let me just clean it up a little bit. Clean it up a little bit like so. Great. So now for this one in green, which is a rectangular, will have this height there as area. The magnitude of this equivalent force is just area under the load diagram, which is equal to 100. It's equal to 100 times the length of this rectangular, which is 9, and this just gives us 900 pounds, right? And then this triangular is a 300 minus 100, so this one is going to be equal to, let me write it in black. I think in black it's not very visible, right? I think let me change this. It's not very visible, this yellow to me. Let me put it in black like so, and also change the arrow in black. Great. All right, there we go. So this one is going to be equal to 300, that is the height of the triangle, okay, minus 100, right? You see, it's 300, this one here minus 100, then we find this height. This is the height we're interested in. Get it? Great. Okay, minus 100. Let me start with the half. So half, that's the area under the triangular loading. Half times the height, which is 300 minus 100. 300 minus 100, then times the length, which is a 9. All right, so this becomes 300 minus 100 is a 200. Half over 200 is 100. Then 100 times 9 becomes a 900. 900 also, right? 300 minus 100 is 200. Half of 200 is 100. 100 by 9 is 900. Great. So let's go to this one. This one is also triangular. So we have half times. This one is 300 minus 50. You've seen this one here. Okay. 300 minus 50. Okay. Is that fine? That's 300 minus 50. I move it a little bit this side. 300 minus 50, and then times the length. The length of this is how much? 12. So therefore this gives us 300 minus 50 is how much? It's 250. So 300 minus 50 is 250 times 0.5 times 12. So we have a 1,500 pounds. Great. And then we have a rectangular, which is just a 50 times the length, which is 12. And then this is supposed to give us how much? It's supposed to give us a 600. All right. So we have all the loads. So let's just put now the lengths. So the length of each one of these here for the rectangle is half of 12. So it is half of 12, which is just equal to 6. So this is 6 feet. Okay. And then let me also indicate this. This will be vital at this point here. Let me indicate this. This will be vital. All right. And then let me find this for the triangular. For the triangular, this one here, this one is going to be equal to This one is going to be equal to one third of 12, okay, which is equal to 4. Okay, so this is a 4. So if this is a 4 and this is a 6, so 6 plus 4, 10, then 4 minus 10, therefore this is a 2 here. Alright, then this one here, um, this one here, okay, this one is going to be equal to that is one third one third of the length for the triangle, which is 9. So therefore this becomes 3 feet. Therefore this is 3. Alright, and then this one, it is just, for the rectangle, it is just half of 9, which is just equal to 4.5. So if we know 4.5, we know 3, which becomes a 7.5, and the 7.5, this one therefore is equal to a 1.5, because we are subtracting from 9, right? Okay, so 4.5 plus 1.5 plus 3, we have a 9. Great. So I think we have everything that we need. What we need to do now is to find the summation of forces in the y, and then later on write this using our equation, which is the resultant in the y times d is going to be equal to the summation of moments about point O, and then we find what d is. Alright, so we have the summation of forces in the y going up in our reference, and we are saying this is going to be equal to the resultant in the y direction, which is equal to we have a 600, we have a 1500, we have a 900, and we have another 900, and therefore FRY is just going to be equal to 600 plus 1500 plus 900 plus 900. This gives us 3,900 pounds. Right, then let's take the summation of moments about point O. About point O, what has happened? Sorry. Summation of moments about point O and clockwise being our reference. What do we have? We have a 600 positive moment by 6 plus a 1500 by 2 plus 6, which is 8, plus a 900 by, what's the lever arm? 900, this is 3 plus 4, that is 7, plus 2, that's 9, then plus 6, that's 15. So this is 15, right? 6, 8, 12, 15. Great. Then finally, plus another 900 times, this becomes a 16 point, a 16 point, a 16.5. Great. Then our moment about point O is just going to be equal to 600 by 6 plus 1500 by 8 plus 900 by 15 plus 900 by 16.5, and this gives us a 43,950 pounds feet. Okay, pounds feet, and this one is anti-clockwise, which is positive. So now we are going to use this particular formula, the resultant force Fry times D, okay, which is going to be equal to the summation of moments about point O. Alright, we found already, of course, we are saying the direction on the left, the direction of the moment on the left should be equal to the direction on the moment on the right. When we are using the scalar methods, we have to always follow the directions, because we are saying the direction on the left hand side of the equation must be equal to the direction of the moment on the right hand side of the equation. Okay. So the one that is giving us the direction is this result we found for the summation of moments about point O. We found that the summation of moments about point O is a positive moment, and by positive we mean our convention we chose is a moment that is in the anti-clockwise direction. Counterclockwise direction is considered positive, and we found a positive value of 43,950 pounds feet. So we expect the moment on the left hand side due to Fry times D to also be positive. So let's now bring in the values. We found a 3900, then we are saying times D. This is going to be equal to the summation of moments. We found a 43,950, and therefore our D is going to be equal to 43,950 divided by 3,900. This gives us a D of 11.27 feet. Okay, so this is where we expect the resultant to be. So if I was to indicate the resultant, we're saying it's going to be somewhere there. I'll indicate it up in red. It's going to be approximately somewhere there. All right, so we are saying this is our resultant in the Y, which is equal to 3,900 pounds, and this position measured from O, this position measured from point O is equal to this position measured from point O is equal to 11.27 feet. Okay, so this is the value of D that we found. So this value of D is equal to 11.27 feet. All right, I think this is about it. Let me just outline this final solution, which is D, and the resultant force that we found. Okay, I think this is about it. We've located the equivalent force, and we've specified this location measured from point O. And I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.